Hey guys, so in the last lecture, we have seen different cases for zeta, that is damping factor. That is, if zeta is equal to 0, that is the system is undamped, so there is no damper in the system. If zeta is less than 1, means the system is underdamped. If the zeta is greater than 1, means the system is overdamped. And if zeta is equal to 1, means the system is critically damped. So we have seen each and every case, and we have also seen the graph of time versus amplitude, how when zeta increases, the damping becomes very much effective and the amplitude just drops very quickly. So that we have seen through a graph, and we have also seen and found the constants using the boundary conditions. That is, if at time t equals 0, that initial amplitude is x0, and time t equals 0, initial velocity is maybe direct, maybe x dot 0 or equal to 0. Literally the initial velocity is 0. So using that, we have found found the constants c1 c2 and used to find the general solution. So that we have seen in the last lecture. So today we are going to uh, take another topic, that is logarithmic decrement. So as the name suggests, logarithmic decrement, that is log of a decrement. So what is decreasing? So amplitude is decreasing due to the damping effect. So how it is decreasing? So it is decreasing by some factor at each and every cycle. So the definition of the logarithmic decrement is the natural log of the ratio of any two consecutive amplitudes, any two consecutive amplitudes on the same side of the mean position, on the same side of the mean position. So suppose this is the graph of amplitude versus time. Suppose, so as you can see that amplitude is getting decreasing. So what it is saying, that natural log of ratio of any two consecutive amplitudes. So which two consecutive amplitudes? This and this, and or this is suppose 1 and 2, or 2 and 3. So either of the any amplitude. So consecutive amplitude on the same side of the mean position. So this is the mean position, and on the same side. So we can't take this amplitude and this amplitude. So on the same side. So that is the definition of logarithmic decrement. So let's frame the formula. So the formula is delta, is the notation for logarithmic decrement, which is log to the base e, because it was written natural log into bracket x1 upon x2. So here we can write x1 upon x2, or x2 upon x3, or x3 upon x4, or anything. So we can write anything. Now if I write the value of x amplitude in terms of n and phi, so we will get that n e raised to minus omega n zeta t divided by n e raised to minus omega n zeta 2t. So 2t means So what is t? T is time period. So in one time period, one oscillation has taken place. So two time period. So two oscillation uh, has taken place. So after two time period. So this will be the solution. So if I just solve this, so what I will get is log to the base e, so n gets cancelled and this goes up, so minus omega n zeta t plus omega n zeta 2t, so this will become e raised to omega n zeta t. So log of base e to e, so delta will be equal to omega n zeta t. So this is the formula for logarithmic decrement. Now t is a time period. So let's convert it into frequency. So as we know that twice pi f. So as we know that time period t is equal to twice pi f. Sorry. Uh, as we know that 2 pi by t. So let me say it again. So as we know that angular frequency omega is twice pi f, and what is f? Frequency is 1 upon time t. So if I want to find t, so t, sorry, t, I can write it as twice pi by omega. So instead of t, I will write twice pi by omega. So here I will write zeta twice pi by omega. Now here this frequency is which frequency? Natural frequency or damped frequency? So here the frequency is damped frequency, which is getting reduced. So what is the formula for damped frequency? So damped frequency formula is omega n under root 1 minus zeta square. So omega n zeta twice pi. So omega n get cancelled. So we are left with delta is equal to twice pi zeta upon under root 1 minus zeta square. So this is the formula for logarithmic decrement, that is twice pi zeta upon under root 1 minus zeta square. Now we will derive another formula based on the definition. So as we have said that consecutive, the ratio of consecutive amplitude would be same, that is geometric mean. So x1 upon x2 will be equal to x2 upon x3 will be equal to x3 upon x4 and so on. So uh, let's take the geometric mean, that is first term. So x1 x3 is equal to x2 square. So if I divide both the equations by x3 square, so I'm left with x1 by x3 is equal to x2 by x3 whole square. So now if I take log of x1 by x3, so this x2 by x3 is not but nothing but x1 by x2, so I can write it x1 by x2 whole square. So what we have got conclusion that first amplitude and the last amplitude, if we are taking the ratio of first and last amplitude, so we can get the ratio of consecutive amplitude raised to the power of difference between these two amplitudes. This is 3 minus 1, that is 2. So that is log to the base e of x1 by x3 is equal to log to the x1 by x2 whole square. So you can write as 2 log e to the base x1 by x2. What is this? This is nothing but 2 delta. So you can write here it as general form. So this is log e x1 by x3. So we can write general form that log the x1 by xn is equal to n minus 1 into delta. So here it was 3, so you got here 2. So if it is n, then n minus 1 into delta. So delta will be equal to 1 upon n minus 1 log to the base e x1 by xn. So this is the formula for logarithmic decrement. So here we have derived two formula for logarithmic decrement, and both the formulas are very much important for examples and for exam point of view. So first formula is 2 pi zeta upon root 1 minus zeta square, and the other formula is 1 upon n minus 1 log e x1 by xn. Now we will see, as we have seen an equivalent spring system, we will see equivalent equivalent damper system. So let's take a mass m, and it is being supported with the help of two dampers, let's say C1 and C2, and it is supported, these dampers are attached with a fixed support. Now as suppose the force is acting from upward direction, so this force if I were to calculate, so in reverse direction this damping force will be acting on it. So this will be C1 x dot plus C2 x dot. So now we can replace F with the help of x dot into C equivalent. So we'll get C1 x dot plus C2 x dot. So you can write it as C equivalent is equal to C1 plus C2. So this is the case for parallel systems. Now for series system, so if the damper are in series, so what we'll get is, suppose force is acting in this direction, so this is one damper and this second damper, so having damping coefficient C1 C2, it is attached to a fixed support. So here force F will be equal to C1 x dot 1, which will be equal to C2 x dot 2, and which will be equal to C equivalent x dot. So here x dot is equal to x dot 1 plus x dot 2. So if I make a subject of x dot with f, so suppose if I make a subject of x dot 1, so x dot 1 will be f upon c1, so you can write f upon c1. Similarly here x dot 2 will be f upon c2, and f here c equivalent x dot will be f upon c equivalent, so ff gets cancelled, so we are left with 1 upon c equivalent is equal to 1 upon c1 plus 1 upon c2. So this is similar to the springs, or we can say resistance, capacitance in parallel series. Similarly we have got the series and parallel connections, so it is opposite to the resistance, that in resistance in series it is added and parallel it is 1 upon ratio. So here it is opposite to the resistance, but similar to the springs. So this was an equivalent damper system. Now we will see few examples regarding this equations which we have solved. So now we'll see an example here. So it is given in question a vibrating element or system is defined by the following parameters of mass m equal to 3 kg. So here it is given in sentence, the symbols are not given in questions, so you need to remember the symbols. So mass of 3 kg, spring stiffness of 100 newton per meter, damping coefficient of 3 newton second per meter, and determine first the damping factor, second the natural frequency and the damped frequency, third logarithmic decrement, fourth the ratio of two consecutive amplitude, that is n xn divided by xn plus 1, and last the number of cycles, so number of cycles after which the original amplitude becomes the 20% of its initial amplitude. So this is our question. So what it is said to find first? So first I have to find, suppose, zeta. So I have to find zeta. So what is the formula for zeta? So it is c upon cc. So do we have both the terms? So c I have, that is 3 newton second per meter, but cc I don't have. So I need to find cc first. So how I can find cc? What is cc? So cc is critical damping coefficient. So what is its value? So the value of cc is, so here we have just found out that cc is equal to 2 under root 100 into 3. So that is 2 under root km, so that is 20 root 3. So we have got the value of cc as 34.64. So we have used this value of cc here in zeta. So we have got 3 upon 34.64. We have got zeta as equal to 0.0866. So now we have found zeta. Now our goal is to find omega n and omega d. So for omega n, we know the formula is under root k by m. So what is the value of under root k by m? So k by m will be equal to, so this will be equal to 5.7735. So as we have found out the value of omega n, but we need to find out the value of omega d also. So what is the formula for omega d? So omega d formula is omega n under root 1 minus zeta square. So what is the value of zeta? So zeta value we have 0.0866 and omega n value we have 5.7735. So we will use these values, 0.0866 square. So we will get the value of omega d, that is equal to omega d is equal to 0. If I want to find in terms of frequency, so that will be equal to 0.195. So this is the linear damped frequency, that is 0.915. So after finding omega d, as we know that omega is twice pi f, so if dividing by 2 pi we will get this value. So what is next? So we have found omega and omega d. So next is logarithmic decrement delta. So how we can find this logarithmic decrement delta? So now only we have seen two formulas for logarithmic decrement delta. So the first formula is related to the damping factor. So we will use that formula directly to find the value of delta. So what was it formula? So the formula was 2 pi zeta upon under root 1 minus zeta square. So we will use this formula. It is 2 pi zeta upon under root 1 minus zeta square. So as we have the value of zeta, So we can directly find the value of logarithmic decrement, so it will come 0.546. So we have found the value of logarithmic decrement. Now the ratio of consecutive amplitude. So to find this, as we know, we also have the second formula for delta. So it is 1 upon n minus 1 log e x1 upon xn. So, or as we know by the definition of logarithmic decrement, delta is equal to log e x1 upon x2, the consecutive amplitude. So if I want to find x1 upon x2, I just have to take exponential on both the sides. So here the value of delta is 0.546, so here it will be e raised to delta, so that is 0.546. So e raised to delta 0.546, which is equal to x1 upon x2. So I have got x1 upon x2 as e raised to 0.546, and its value is 1.727. So this is the next thing. Now at the last, I have to find the value of n, that is number of cycles, which the original amplitude is reduced to 20%. So what it is saying, so suppose the initial amplitude is suppose x1, and final amplitude is suppose xn. So it is saying that xn is equal to 0.2 x1. So now if I want to find then how many number of cycles it has taken to reach that, so as I know that the formula for logarithmic decrement for number of cycles, it is 1 upon n minus 1 into log to the base e upon x1 upon xn. So I will use this formula to find how many number of cycles it has taken. So let's start. So x1 upon xn, the ratio, if I want to find, so it will be equal to log the base e, that is 1 upon 0.2. So 0.2 is nothing but 2 upon 10. So it is nothing but log of phi. So it is log of phi upon n minus 1 into delta. Now we know the value of delta, so we can find the number of cycles. So what is the value of delta? So the value of delta is 0.546. So we know the value of delta, that is 0.546. So n minus 1 will be equal to log phi divided by 0.546. So this will be equal to nearly 2.947 something. So n will be equal to plus 1, so that will be n equal to 3.947. So nearly after 4 cycles it can reach to that amplitude, that is 20% of its initial amplitude. So it has diminished 80% in nearly 4 cycles only. So this is the power of damping coefficient, damper. So we'll see a few examples also in the next lecture. So thank you very much.